Hey everyone, and welcome. Today, we are diving deep into something pretty incredible. We're going to crack the code of the universe itself by exploring partial differential equations, or PDEs. Now, these are basically the mathematical sentences that describe everything, from the ripple of a pond to the heat flowing out of your morning coffee. But, having these elegant equations is one thing. The real question is, how on earth do we actually solve them?
So let's start with a really famous one, the heat equation. This beautiful little formula describes how temperature, which we're calling U here, changes over time and across space. It's literally the reason the handle of a spoon gets hot when you leave it in your tea. The equation looks so simple, so elegant, right? But the big mystery is, how do we get from this abstract set of symbols to a real concrete answer? How do we solve it? So here's our game plan. We're going to build a powerful mathematical toolkit piece by piece. We'll start with what these equations are all about, then we'll work our way up through more and more powerful methods, from simple integration to some really clever transforms, and finally, we'll unlock the ultimate key using the magic of complex numbers. Okay, first up, let's just take a moment to appreciate what we're really dealing with here. These PDEs, they're not just abstract math. They are the actual language that physicists and engineers use to describe and predict reality.
I mean, the sheer scope of what these things can describe is just mind-blowing. They're at the heart of fluid dynamics, acoustics, electromagnetism, even the stock market. But here's the catch. For all their power, they are a real beast to solve. That's because they're juggling multiple things that are all changing at the same time. There's no single magic bullet for solving them all.
So if we want to solve them, we need a toolkit. And like any good mechanic, we're going to start with the simplest tools first. Let's take our first steps into finding a solution.
Our very first tool is direct integration, okay? Think of this as your trusty wrench. For the simplest, most straightforward PDEs out there, you can just integrate the equation one variable at a time, kind of like you did back in basic calculus. It's clean, it's simple, but it really only works for the most basic problems.
So what happens when the problem gets a little bit trickier? Well, we grab our next tool. This one is called Lagrange's method, and it's specifically designed for a very common type of equation that fits this particular pattern you see here. It gives us a really clear recipe to follow.
And the method itself is this awesome, systematic recipe. First, you set up a related set of much simpler equations. We call them auxiliary equations. Then you solve those to find two separate solutions. And finally, you just combine those solutions to get the whole answer. It's a fantastic step-by-step process, but only for that specific class of problems.
But that brings us back to our original challenge, right? The heat equation. Direct integration? Nope, won't work. Lagrange's method? Not the right format. Our simple tools just aren't going to cut it here. The problem is too complex. We need something more powerful, something more clever in our kit.
And this brings us to the next level of sophistication: transforms. The core idea here is absolutely brilliant. If you can't solve a problem the way it's presented to you, why not just change your perspective? Look at it in a completely new way.
A classic technique here is the method of separation of variables. The genius move is to assume that your complicated solution is actually just a product of several simpler functions, where each one only depends on a single variable. This lets you split one really hard PDE into a bunch easier to solve ordinary differential equations, or ODEs. It's incredibly powerful, but often the final answer means you have to add up an infinite number of things, which, creates its own little headache.
But for a truly revolutionary change in perspective, we turn to the Fourier Transform. This is a total game changer. Instead of looking at a function's value over time or space, the Fourier Transform breaks it down into the basic frequencies it's made of. It's kind of like hearing a musical chord and being able to pick out each individual note.
Think of it this way. Looking at a problem normally is like trying to track every single little wave on the ocean's surface. It's just chaos. The Fourier transform is like stepping back and seeing the big picture, the underlying rhythm, the tide itself. By switching the problem into this frequency domain, a ton of really hard PDEs suddenly become way, way simpler to solve.
So, changing our perspective can simplify complexity. That's a huge deal. But is that the end of the road? Is there an even more powerful, maybe even an almost magical tool out there? One that connects completely different parts of math to give us the ultimate key?
Oh, you bet there is. For our final act, we dive into the beautiful and incredibly powerful world of complex analysis. We're talking about using numbers that involve the square root of -1. Now, I know that sounds super abstract, but trust me, it provides the most elegant and powerful key of all.
To understand this key, we just need a couple of new ideas. First up, a singular point. So, imagine most functions are like smooth, predictable paths. A singular point is a trouble spot on that path. It's a gap, a sharp corner, a place where the value just goes wild and shoots off to infinity. It's where the normal rules just break down.
Now, a really common type of singularity is what we call a pole. You can think of it as a specific spot where the function's value blows up to infinity. We're especially interested in what are called simple poles, which are the most basic kind. These poles are like little treasures on a map that we need to find.
Okay, now for each one of these special points, these poles, we can calculate something called a residue. And this is the cool part. The residue is a single complex number that magically contains all the important information about how the function is behaving right around that trouble spot. It's like a numerical fingerprint of that singularity.
And that brings us to the grand finale, Cauchy's residue theorem. This is honestly one of the most powerful and beautiful results in all of mathematics, and what it says is just shockingly simple. It says that a really difficult calculation, this integral around a closed loop, can be found by just adding up the fingerprints, the residues, of all the trouble spots inside that loop and then multiplying by a constant. That's it. The power of this theorem is just how simple it makes things. It transforms a mind-bending calculus problem into basic arithmetic. Seriously. All you have to do is find the trouble spots inside your path, calculate their little fingerprint, their residue, and just add them up. It is an unbelievably elegant shortcut that cracks problems that used to be nearly impossible.
So let's just recap the journey we've been on. We've built this incredible mathematical toolkit from scratch. We started with the simple wrench of direct integration. We added the specialized tool of Lagrange's method. We learned the clever trick of separating variables, got a whole new perspective with Fourier transforms, and finally, we unlocked the ultimate power tool with residue calculus from complex analysis.
At the end of the day, these are so much more than just equations on a slide. They are the keys to understanding the fundamental patterns of our universe. From predicting the weather to designing the next smartphone, solving these equations allows us to model, predict, and ultimately shape our world. So the only question left is, what will we unlock next?